Functions, the lifeblood of mathematics. Going to start off with some definitions. A relation. Now, a relation is simply a rule that maps between two sets of values. For example, there you go. All those green lines are mapping from the x values to the y values, and some of them are going back the other way as well. A relation that describes that particular one would be x squared plus y squared equals 5. Now, a function is a very special type of relation because it uniquely maps from a set of values to another set of values. Something like that. See, it's unique. Each x value only goes to one particular y value. Sure, multiple x values can go to the same y value, that's fine. But it's the x values mapping uniquely. That particular one, y equals x squared. An independent variable. So it's like the input of the function. So it's what we're putting into the function. Now, the domain is all the possible values of that independent variable. Everything that's possible to put into our function and get an answer. The natural domain is everything that we can do. Sometimes we have restricted domains, because sometimes it's possible to substitute numbers in, but not useful. The example I've given there is maybe we're dealing with time. So it's logical to use t greater than or equal to 0. We're not really interested in negatives in a lot of cases. So that might be a case where we restrict the domain. Dependent variable is then the output, because its value depends on what you inputted. So that becomes the dependent variable. Then the range of a function then is all those possible dependent values. If you did substitute in every possible input, so all the domain, every value, what is the output? That's your range. So that brings us to function notation. You would have seen it before, something like this. Y equals f of x. So the independent variable is what you're inputting. So it goes with the, where I've got the x. F is defining the rule. So that's our function, whatever the rule happens to be. And then what we make the subject of it is the dependent variable. So the value of y will depend on what the function is and what we're substituting into the function. When you draw a graph, you always put the independent variable on the horizontal axis and the dependent variable on the vertical axis. Possibly that's been explained to you in science. But that explains why the x-axis is horizontal and the y-axis is vertical. Because in the bulk of our functions, we usually go y equals whatever. So function x is 3x squared plus 4. Our input is going to be 5. It really is just a substitution question. Sub 5 in, and we get 79. Of course, you don't have to substitute in a number. It could be another pronumeral. Everywhere I see an x, I replace it with an a, so it just becomes 3a squared plus 4. Doesn't have to be one pronumeral. I can do something like this. Function x plus h minus function x. Everywhere I see x, replace it with x plus h minus, I'll substitute the actual function itself, expand out, tidy it up, 6xh plus 3h squared. So how do we tell if something is a function or not? Knowing the picture is the easiest way. And that's why we'll spend a lot of time working out how to recognise basic functions and how they change depending on what we do with the equation and so on. Because if you can visualise it, real easy to test. Vertical line test for functions. Basically, if you draw a straight line parallel to the y-axis, it'll only cross a function once, if at all. If at all. So imagine sliding a ruler along the number plane. As soon as it hits it twice, it's no longer a function. So here's our hyperbola. We can start at the left-hand side. It hits it once. Everything's good. We get to the y-axis. It doesn't hit it at all. That's okay, because it's a maximum of one time, so not hitting it's all right. We keep going. So that one, it doesn't matter where we draw in that vertical line, it could only cut it once, if at all. So yes, there's a big tick. That is a function. Parabola on its side, so x equals y squared. I start out at the left, everything's fine. It's not touching it, it's not touching it, it's not touching it, that's fine. I get to the y-axis, touches it once, still okay. As soon as I move past that y-axis, I hit it twice. No good. It's not a function. No, it's not. So if you've got a visual picture of the function, real easy. Actually, this one here, it's two functions joined together. So y equals the square root of x, which would be the top half of the parabola, and y equals minus the square root of x, which would be the bottom half of the parabola. Domain and range. So let's generalise it for y equals function x. How do we find the domain of a function? As I say, if you see the graph, fantastic. You can do it. So again, let's put that parabola on the side. What would its domain be? I could just look at it. What are all the possible x values that I could substitute in? And the way you could visualise this is imagine walking along the x-axis and you look up, you look down, can you see the function? If you can, you're in the domain. If you can't, you're not in the domain. So you'd be walking along this one, and it's not until you get values that are greater than or equal to 0, you're going to see that function. Or, sorry, that relation. So the domain for this one is x is greater than or equal to 0. One of these split functions, that's fine. This one, x is less than or equal to 0, but then it skips and it doesn't start up again until 2, but not including 2. So x is greater than 2. That will be our domain. So see the picture? Fantastic. What if we don't recognise it? Then we have to go back to algebraic methods. What do we look for? Well, we look for things that are going to cause problems when we substitute in. The classic ones are fractions. Because what do we know about fractions? Bottom of a fraction can't equal 0. So you have a look at the bottom of the fractions. Is there anything going to cause me a problem there if I substitute it in? Will it create 0? Let's start with the most basic one. Y equals 1 on x. Bottom of the fraction can't equal 0. I do not write my domain like that. Because a domain is when you're telling them what is included. What can be substituted in. It's not telling them what's excluded. Because here I just look at it and they say, x cannot equal 0. Well, that's fantastic, but what can x be? It's not telling me the information. So I'd write it something like this. Oh, well, it's all real x. I can substitute everything in, except I can't substitute in 0. Some people put x cannot equal 0 there, and it all comes down to grammar, I suppose. Both is correct. Because think of it, I'm saying all real x except x equals 0. But some people might read it as all real x except x can't equal 0. It's got the same information, really. Bottom of the fraction can't equal 0. So let me have a look at that. X squared minus 1 can't equal 0. I have two x values that are excluded from the domain this time. So all real x except x equals plus or minus 1. You might have two fractions added together. Both fractions, neither of those denominators can be 0. So I know x minus 1 can't equal 0, but I also know 7 minus x can't equal 0. So we get all real x except x equals 1 or 7. Root signs. And I guess I'm talking about even roots. Odd roots are fine. You can find the odd root of anything. Even roots you can't. You can't find the square root of a negative number. Can't find the fourth root of a negative number, and so on. Mainly square roots, we'll see. Y equals the square root of 4 minus x squared. Let's pretend we don't recognise what that is. I know the square root sign. Well, 4 minus x squared has to be greater than or equal to 0. I just have to solve this inequality, or inequation I should say, more correctly. Solve this inequation to find my domain. X squared is less than or equal to 4. X is in between minus 2 and 2. There's my domain. Ooh, two square root signs. Well, I still can't find the square root of a negative number. So I know that x has to be greater than or equal to negative 3, but I also know x has to be less than or equal to 5. It has to obey both of those for a solution. So therefore the domain is in between minus 3 and 5. Ooh, let's combine the two together. I've got a fraction and I've got a square root sign. Well, all the difference here is instead of saying x plus 2 is greater than or equal to 0, now it has to be greater than, because it can't equal 0 because it's on the bottom of a fraction. So x plus 2 is greater than 0. There's my domain. X is greater than negative 2. They're really the two key things to look for with domain. That's say, if you know the picture, makes life real easy. Well, what about range? Again, if you know the picture, let's go back to x equals y squared. But this time, we're climbing the y-axis. So when we climb our y-axis with this one, I'm always seeing this relation. So the range is all real y. It's important you say real y because they're real values. I mean, there are other types of values, but we won't go into that right now. Don't just say all reals, okay? Because when someone's asking you the range and you say all reals, then we don't understand whether you know it's the x values or the y values, which is domain, which is range. So you need to mention all real y. There's our split function. That one will be y is less than or equal to 1 and y is greater than 3. Okay, we don't know what it looks like. What do we look for here? Maximum, minimum values. How high can the function go? How low can the function go? See, we know things like this. We know that even powers will always be positive. When you square a number, you're going to get a positive number. Similar thing with absolute values. They're always positive. Those sorts of things might restrict how high up or how far down it goes. Start with the basic, y equals x squared. Well, I know the range for that must be greater than or equal to 0 because x squared is always greater than or equal to 0. So that's the only possible answers we could get. So logically, if I've got x squared plus 3, well, I know that one must be greater than or equal to 0 plus 3. The x squared can't be less than 0, so then the whole thing can't be less than 0 plus 3. Range y is greater than or equal to 3. 5 minus x squared, but hang on, now it's minus, I'm taking it away. So the biggest it could be would be 0. So in this case, the biggest it could be would be 5 minus 0. Absolute value, x plus 2, absolute value, got to get a positive number. Y greater than or equal to 0. What about if we shifted that curve? X plus 2, well, the x plus 2 has got to be bigger than or equal to 0, but we're subtracting 5 from every answer. So the smallest I could have there is negative 5. Y's got to be greater than or equal to negative 5. So there's some sort of ideas you use algebraically when you're looking for a range. Restrictions on the domain are interesting because remember the range is every possible number you can put in. So maybe there was a restriction on the domain. Rule of thumb, sub in the endpoints. I usually sub in the center. It's amazing how many of these things turn out to be symmetric. And so it usually gives you a good idea of what the range is doing. So to go back to our 4 minus x squared, remember? We said the domain for this one was in between minus 2 and 2. So my domain is restricted. If I sub in x equals 2, I get 0. If I substitute x equals 0, I get 2. I don't think I bothered substituting in negative 2 because clearly negative 2 will give me the same answer as 2. So from that I'm going to conclude that the range is in between 0 and 2. And if you recognise what our function is there, yeah, well, of course it is between 0 and 2. Fractions. Okay, well, how does this affect range? If you've got a constant on the top of the fraction, that fraction can't equal 0. So you can't get 0 out as an answer. Go back to y equals 1 on x then. This function could never equal 0. It doesn't matter what you substitute in, you're not going to get the answer 0. So therefore, the range is all real y, except y equals 0. 5 plus 1 on x then, well the 1 on x can't equal 0, so the whole function can't equal 5. Ooh, x plus 7 on x plus 4. This is an interesting one, because you may not see it straight away. If you do yourself a little division there, or split up the fraction, you get 1 plus 3 on x plus 4, it becomes more obvious now, because the fraction now has a constant on the top. So that fraction can't equal 0, therefore, oh, there's the polynomial division, by the way. If you really want to do it the long way and go, how do I get that? So that function can't equal 1 plus 0, so there's my range, all real y except y equals 1. All right, 3A and 3B, time to play.